So guys, as I have said yesterday, I guess, or the day before yesterday, that these lectures are for your reference. Some of them is going to be theory, but very few things, but the rest are just for your reference. What does this mean? It means that when I ask you to do some analysis and you want to see whether there is a relationship between the consumption of fuel of a certain car and the type of the car or number of cylinders or blah, 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 you have a data set about this. So you know that there is a relationship or not through some visualization. If I ask you, for example, this example that we always see, whether there is a relationship between the size of the apartment and the price of the apartment, you would be able actually to show me some visuals in front of me as your manager that, look, this is actually the relationship between this and that. Okay, so again, you will see a lot of things here, and I have included a lot of things here, not to be memorized at all, just to know that we have these graphs, and this is the code, and you can use it. Clear, guys? Okay. So today we're going to talk about visualization again, but this time we're going to talk about a relationship between two variables, and instead of univariate, we're going to talk about what? What we're going to talk about? Exactly. Bivariant. Okay, guys? So we're going to talk about bivariant. So a question in the test, let's see. We have univariant and bivariant. What is the difference between them? That's it. You got 1 grade, for example. Okay, and the answer is you got 1 grade. So you will see that the answer is that, and one of the answer is going to be you got 1 grade, and you're going to click this answer, okay? Look at it here. Look at the slide. What does it say? What is univariant? And what is bivariant? Okay, so when we change the level or value of one variable, what kind of changes do we expect from the second? This is actually what we have talked about. We said that, for example, the size of the apartment has changed. What's going to happen to the price? Is it going to increase, decrease, stays the same, blah, blah, blah. Okay, we have 4-cylinder, now I have 6-cylinder. Depending on the data that I have collected, okay, the consumption of fuel is going to increase or decrease or not changing for. Okay, that's what does it mean, what do you mean exactly? Are there a consistent pattern or trend? Is it like increase, increase, decrease, decrease, or sometimes maybe no? Sometimes according to the data that you have collected, you will see sometimes increases and sometimes decreases, so there is no trend or pattern. Are there multiple clusters in which our data points fall? And this is actually that I have shown you in the first lecture, if you remember, when we have done some analysis on the satisfaction of the customers. And we said that we have customers that are satisfied and loyal, other customers that are satisfied but not loyal, other customers that are loyal but not satisfied, and other customers that are both satisfied and loyal. Do you remember this? So these are called the clusters, and this is what we talked about. Are there multiple clusters in which our data points fall in, or no, actually they are everywhere. And we would be able to detect these things using what? Using these visualizations that I'm going to show you quickly today. And as I have said, I want these things to be a reference for you. And if you do more analysis to your data and show me more things, especially if they are related to your research question, this is going to give you a bonus in your assignments. So we'll look at 3 major bivariant plots. We will plot first of all whether we have a quantitative versus a quantitative. And can anyone, yesterday I asked you the same question. When I say quantitative, can anyone tell me anything about these, an example of these 2 variables, for example? Sorry. Versus quantitative, it means the 2 variables are numbers. I have given you 2 examples right now, if you remember. One of them is the size of the apartment with price. Okay, this is what? Quantity or quality? Quantity. So quantity versus quantity. Or I can have quantity versus quality. Okay, can anyone give me an example, for example? So for example, the satisfaction, somehow level of satisfaction is going to be good, bad, or blah, blah, blah. Or for example, if you remember, I have given you what? The car. Just right now, I said that we have cars which are 4 cylinders, car which are 6 cylinders, car 8 cylinders, car, and the fuel consumption. So this one is qualitative and the other one is quantitative. Qualitative versus qualitative. So both variables are qualitative, and we want to see whether, let's say, 8 cylinder, 6 cylinder, 4 cylinder, whatever, and the type of the car, Mercedes, BMW, blah, blah, blah. So this is quality versus quality. We'll also learn about bivariant plots, types to summarize your data, and how to adapt univariate plots to some bivariant. So the thing that we have seen with one variable, how to use them in order to see the second variable. So if you want to inspect a relationship between two numeric variables, again, two what? Numeric. That's why it's important to know what is the type of the data that you're dealing with. Now we're dealing with two numeric. What do? You choose something called scatter plot. Is this clear? This is scatter plot when you have two numeric values. In a scatter plot, each data plot is plotted individually as a point, its x position corresponding to one feature, while the y position corresponding to the second feature. And this is usually what we do. I ask you, for example, let's say I ask you for, let's say I have a set of points, if you remember. That's what we have seen even in the high school, x and what? And y, x1, y2, for example. Okay, x2, y, for example, 5. Okay, x0, y, for example, whatever, 1 or whatever. And what do? You usually go to, this is the x-axis and this is the y-axis. Do you remember? 1, 2, what does it mean, 1, 2? It means 1 here and 2 here, and this is the first point. And this is the second point, and this is the third point. And so what do we call such a plot? Scatter plot. Instead of x, let's say I have the size of the apartment. And instead of y, let's say I have the price. And again, here is going to be the size and the price. And as you can see, these points are corresponding to what? To this apartment. So this point, this is the size of the apartment, and this is what? The price. Is this clear? Clear, Dima? So what do we call such thing? Scatter plot. And it's gonna put the x-axis and the y-axis. The x-axis in a numeric and the y-axis is also a numeric. Questions? Okay, so how we create, as you can see, we can use the matplot library, and we can say plt.what? Scatter. What do I have here? The first argument, and here is the x, and here is y. Here is x is equal to, let's say, whatever we have the size, and here this is the price or cost. Here, I guess it's easy. Yes. So I want you to pay attention to this one here. When I draw the data, we can draw something called a regression line. And regression line is a behavior that is going to tell me whether there is a relationship between the x-axis and the y-axis. And as you can see here, I have a certain trend that says that as the x-axis, the value of the x-axis increases, what's happening to the value of the y-axis? Increases. Okay, we can deal with something called Pearson correlation coefficient. I don't want actually you to get like intimidated by the name. He's a statistician, and he has says that we have something called Pearson correlation coefficient. And what is this Pearson correlation coefficient? It's as follows. I have two values, let's say, as the size of the apartment and the price, yes? So when we draw this and we see that there is a relationship between these two, And this relationship, it depends on, actually, it can be one of these three things. It can be perfect relationship with Pearson correlation, usually it's called R, is equal to 1. R is equal to 1, it means that I have a perfect relationship. This increases, this what? Increases, okay? Or R equal to -1. And this means that I have an inverse perfect relationship. The first one increases, the second one is decreases. Is this clear? Okay. And this is actually, if you remember this in chemistry, for example, when you increase the pressure, what's going to happen to the volume? Increase or decrease? Look at it. Increase the pressure. The pressure is increasing. What's happening to the volume? It's inversely proportional. Okay, so this is the relationship between them. One increases and the other one decreases. Okay. Now, if we said 1 or -1, if you remember. What about 0? No relationship between them. This one goes like this one goes like this, so no relationship at all. Okay, but usually, what do? Usually, we don't have only these three numbers. Usually, this Pearson correlation, it can be, for example, 0.8. What do you think? If it's 0.8, what do you think? A strong what? Correlation. Okay. If it's, for example, 0.1, what do you think? Weak. If I have -0.7, for example, you see what I'm saying? So if it's very close to the 1, it means I have a strong relationship between the X and the Y. If it's close to 0, it means weak relationship or no relationship. If it's close to -1, it means strong relationship, but in the inverse. Is this clear, Khadija? Okay, that's what we call what? Pearson correlation coefficient. That's it. It's not a big deal to us, but there is a question, in multiple choice about this. Not in this, but in the final. You see, when I said there is a question in the final exam, you see, I told you, Abdurrahman, there is 2 questions in the final exam about the Pearson correlation. So a Pearson correlation, as you can see, it's a part of statistics we use to quantify the strength of a linear correlation between 2 numeric variables. So I have 2 numeric variables, and the simplest one is the size of the apartment with the price. This is a numeric, and this is a numeric. So I want to know whether there is a correlation between these. What does it mean, a correlation between these? It means that if the sizes increases, for example, is this one is going to increase or decrease, or it has no change, or what? So in order to know this, we have in statistics something called R, and this is for Pearson, and you can see R is for Pearson. And this R can take any values between -1 and what? And 1. 1 means perfect correlation. If this increases, this increases. -1 means we have correlation, but in the opposite. If this increases, this is going to happen, decrease. 0, it means if I got a number which is close to 1, it means I have high correlation. If I got number which is close to -1, it means that I have inverse correlation. If I got number which is close to 0, what if I say, for example, is 0.3? I said that the correlation between the size and the price is 0.3. What do you think? Is this high correlation, weak correlation? We cannot tell. It's neither high. What do you think? What do you say? This one is close to 0. If it's close to 0, it means weak correlation. Here. So we have no questions in the final about this part. Okay. Now it's clear. Okay. So again, when it comes to the seaborne, remember when we said that we have the matplot library and we have the Seaborn. The Seaborn is the advanced version of the matplotlib. Okay, so it's built on top of it. Seaborn we have this regular plot. As you can see, we have the data, we have the X, and we have the Y, and we have what? A regression fit. Do you remember this when I said there is this line that we in the previous plot, which is the matplotlib, we don't have this regression. We have to do other stuff in order to be able to draw this line. While in Seaborn, all what you need to do is to say, for example, regression fit equal. When you put this one here, you will have the same. These dots are the same, but also it's gonna draw for you this line. And from this line, you can conclude that there is a certain relationship between this variable here and this variable. This one is increasing, and again, this one is increasing. Clear? Okay. So the regression function is a linear and includes a shaded confidence region for the regression estimate. So these are, this is the region. So the regression line can be like this, or can be like this, or can, so all these are included in the regression. Usually it's one line, but here it says that this is the confidence interval. If I go beyond this, so if I draw a regression line like this, outside this one, so it's not going to be, so if I draw a regression like this, outside this shaded area, so this one does not indicate that these are correlated with each other. And thus, actually, there is a method in order to find the best line here. How to get the best line. There is a method that we're going to see later, maybe next week. Yeah, next week we're going to see it. And this is actually what we call a regression algorithm in order to find the best line. By all means, so, yeah, it's gonna say the correlation, and R is gonna be, yeah, for sure. The R is gonna be we can get it from here on. So let's look at this one here. And it says that, as you can see, these numbers are very small, 1, 1.5, 2, 2.5, 3, 3.5. These numbers are small, and these numbers are big, as you can see, 100, 200, 300, and 400. Sometimes we do something called log transformation. I don't want to bother you with this, but we'll have an example, because sometimes I'm comparing the x-axis, the numbers are very small, the y-axis are very big, okay? And sometimes it's the opposite. Sometimes it's the opposite. Sometimes I have here very small number and here very big number. So I want to do a transformation. That's what we call transformation. And a transformation, it means that I want to get rid of these big numbers and transform them into another numbers, which is small numbers, in a way that this graph is going to look better. So again, when do we do this? When I have one of the axes contains small numbers, as you can see, and the other contains big numbers. We do something called log transformation. We do something called what? Log transformation. Okay, why do we do this log transformation? Let me show you something here. Let's say, for example, I have 1, 0, 0, 0, 0, 0, 0. This is what? I don't know. Let's say we have this number. As you can see, it's a big number. When I say log this number, as you can see, what happened to this number? Instead of million or whatever, 10 million or what, this is actually million. What happened to this number? It's now become 6. So the logarithm, the basic idea of the logarithm function is that instead of having big numbers, I can have what? When I apply this, something called logarithm. And usually the logarithm is something that you have even noticed in your real life. What does this mean, the logarithm? If I ask you, for example, a simple question, I say, I have, let's say, a class of 16 students. Okay, and I want to catch one student of them, but I want to do this using this method. I'm gonna do what? I'm gonna divide this class into 2 subclasses. Okay, and I have now class 1 and the class 2. What do you think? How many students do I have here? 8, and here? Yes? Okay, I'm gonna check. Oh, my student actually that I'm looking for is somehow his age is less than a certain age, and these are sorted. So I know that I have to look here. Let's say, for example, and I need to divide this into how many now? 4, and this one is 4. And what do you think? This one is going to be divided into 2, and this one into, and this one into, and this one into, and this one into. How many do I have now in this class? How many students do I have? 1. And in this class, 1. So how many steps it took me in order to get from 16 into 1? Let's look at this part here, and let's write 16. Look, okay. I know what's happening. Let me go here, and let me, for example, put log of base 2. Why base 2? Because we divided each one of these into what? Into 2 of 16. What is the answer? Can anyone tell me what is the answer? What is the answer? If you remember the number of steps that we needed, how many steps that we needed? Look at them. 1, 2, 3, and 4. We needed 4 steps in order to go from 16 into 1. The same idea. If I put 1 million, for example, what was the answer that we got it? So do you know what's going to happen? It means that I needed 6 steps in order to go from, actually it's more than this because it's base 10. Base 2, it means 1 million. The next step is going to be what? 500. The next step is going to be the 1. How many steps do I need in order to get to 1? The 1 million, I guess 9 point something or maybe 11. So if I put look of 1 million, 1, 2, 3, 1, 2, 3, enter. How many steps? 19 steps. Just 19 steps, I can get you from 1 million into 1. That's what does it mean actually, and we use this a lot in programming, this logarithm function. So what does this mean here? Instead of having one small number and one big number, what do I do, Fatima, to the big number? I apply the logarithm to this big number. And this big number, when I apply the logarithm, what's going to happen to it? It's going to be a small number, but it's going to preserve its properties. And you will see this, and you can draw the graph. Clear? Is this clear? So what do I do this log transformation? When I have what? One of the axes is big. Okay, and usually the y-axis. Okay, so let's go back to this one here. Let's go back to this one here. And this is the method. This is a method that we're going to use in order to do some log transformation. It's very easy method, and you can apply it directly. What is the method? All what you need to do is to send for me the data frame, and then after that, I will apply this numpy.log10x. It means that converts this into logarithm, and this logarithm is of base 10. We can put 2 at base 2 and so on. But let me understand this a little bit with you guys, so when you read it, to understand what's happening. Here we have a very important function is called apply. First of all, daemon. Look at this one here. What does this mean? It means that create for me a method. So I'm writing now just like a method in Python. Create for me a method. This method is called, you give it whatever name you want, and we said we give it a meaningful name. What is the name of the method? Log transform. And what is going to take? X. So that's all what I need you to do. Define a log underscore transform, and it's going to take X. Forget about the rest. Now the rest is not there. Return mp dot what? Log of base 10 of what? Of X. So now what does this mean? It means that if you give me a number, I'm going to return for you what? the logarithm of that number. Is this clear? So this code is actually what's happening. You give me a number, I'm going to return for you the logarithm of this number. Let's say you give me, for example, you give me 10. What is log of base 10 of 10? 1. So it's going to return what? You don't know. You don't need to know what is log. It's calculator and you put it. But log of base 10 of 10 is equal to what? To 1. So if you give me 10, I'm going to return for you log 10, which is 1. If you give me 100, I'm going to give you 2, because 100 is 10 to power. Forget about. So if you give me something, I'm going to return for you a number, which is much than what you're giving me. Is this clear? So this part here is clear? Is this clear, Ali? Okay. So what is this that you're writing here? Inverse equal false. If not inverse, what is this? Forget about them. They are not there. Forget about them. Now what's we have? We have just this X here, and we have only this part. Return what? So look what's going to happen right now. What I'm going to do is that, remember when we said this part here is big numbers? What do I want to do? I want to apply the log transfer for them. Why do I need to do this? Because I need to get a smaller number from this number. Is this clear? So I'm going to apply to this one here, which is num underscore variable 2. I want to apply to this number here what? The log transformation. And this is the beauty of this apply. Look, guys, if you need to leave, don't come back. Okay, is this clear? This door is making me. So if you leave, don't come back. Clear? Okay. So this apply, usually we give a question like this in the exam. What is this apply? Look, guys, it's very easy to understand it. If I ask you, for example, if I ask you log transfer and I give you 10. So it means call this function, which is called log transfer, and send to it what? 10. It's going to go here. We said we don't have this, we don't have this, we don't have this. It's going to send, instead of X, it's going to send 10. It's going to find for me the log of 10. If I put, for example, here log 20, log transfer 20, instead of X, I will have 20. It's going to go here and replace X and do the calculation and return the value for me. Is this clear? This what does it mean? That's what we have seen in Python. But what does it mean? Apply, and as you can see, what did I write here? The name of the function. When do I do this? I do this. If I have, how many number do I have that I want to apply this function to? How many numbers do I have? I have the 10, I have the 20, I have the 50, I have the 100. I have all these numbers that are here. So do I pass them one by one? Persons, they say, no, don't do this. All what you need to do is, this is the set of numbers, yes? It's inside what? df number variable 2. All the numbers here. How many numbers do I have? 1 million. We don't care. What do you want to do to all these numbers? I want to apply to all these numbers one by one this function here. So how to do this? All what you need to do is to write dot apply. Is this clear? You see how powerful is this? So what do we do here? All these numbers in this column. I have in this column 1 million number. I don't care. Apply to all these columns. Apply to them a transform. Apply to them this method here. This function. And it's going to go and apply one by one and return for you the values of each one. Not all the values of each, as if you have done 1 million call just in one place. Clear? This apply? Okay. So now, what do you mean by this inverse false? And like in our, forget about it. What do you mean by this? We, as I have told you, this is the philosophy of the people on Python, and we're going to use the same philosophy. If you remember, I don't need actually to find the sum of the column, the sum of the row. We put the x's. Do you remember? X is equal 1 and x is equal 0. The same idea here. Sometimes I told you we need to do logarithm. Sometimes we need to do the power. Sometimes I need to minimize the number. Sometimes I need to do what? Instead of minimizing these numbers, I want to maximize these. You see what I'm saying? Sometimes I need to minimize these. Sometimes I need to make these numbers bigger. Instead of 0.3, 0.35, I want to make them bigger. So what do? We apply something called power function. Okay, so what I'm saying here, I'm saying if I want to do power function, all what I need to do is to call this function here. And what do I pass instead of this? What do I pass here? If I pass through, it means that I want this or I want this. Depending on this, I want what? The else. And what does it mean I want the else? Instead of applying the logarithm, shrinking the number, what I'm doing now, I'm getting the number bigger. So I have written one function that is gonna work for maximizing numbers or minimizing. If I want to minimize, I leave this as it is. If I want to maximize, I write inverse equal true. So if I write inverse equal true, if not inverse, what do you think? This is gonna condition true or false? False. So I'm gonna run into the else. Is this clear, guys? Clear or not clear? Okay. It's not sharp incline. It's, we'll see when we do the logarithm. You will see. Actually, do I have it? I don't have it here, but maybe I have it in. Where do I have it? I have it somewhere. Maybe I have it here. So look at this. You see this one here. So I have created for you something that you would be able to play with. So I have created for you two series. Can you see this series? S1, 1.5, blah, blah, blah. And this is what, this is actually the y. So this one is the x-axis, these values of the x-axis and these values of the y-axis. So when x equal 1, y is equal to 30. When x equal 1.5, y is equal to 60. When x is equal to, this one is equal. So I have these values. If I go and draw these values, I will have a relationship, but it's not going to be clear relationship. Because as you can see, these numbers are small and these numbers are big numbers. So what I do, I can apply to these big numbers something called log transformation and do what? And check my graph now after I apply the log transformation to this one. And most probably when I have such cases, the graph will be more clear and you will see the relationship in a clearer way. That's the main idea. So what do? I have written this, the same function that I have shown you. Can you see it? So what did I say? I say that I have a function called log transformation. This is the x that you want to give me and the inverse by default. If you don't give me anything, it's going to be false. It means you want to apply the log transformation. And look, here is the result. I'm saying Sx. What is Sx? What is Sx? The small or the big? The small. What do I want these small, for example? I want to make them. So I'm applying the power or I'm applying the logarithm. What do you think? What do you think? If I have number, I want to make it bigger. I apply power. So for example, I have 2. Let's say 2 power 10 is going to be what? Bigger or smaller? 2 power 10 is going to be 1024. Yes? Okay. So let me get rid of this one here. And let me write, instead of x, let me write y. So what do I want now to do? I want to apply this one here. Yes? So let me run this one here. And let me run this one here. And let me check the result now after I apply. So if you remember, I applied it now on the y. Yes? The y I had 30, 60. Look now what's inside y. What do I have? 1.4, 1.7, 1. Blah, blah, blah. And I have all these. Yeah, because as you can see, this one here is false. by default is false. Okay, guys? So when do we apply this log transformation? Your name. Yeah, when do we apply this? Exactly. When I have to play with my exact. Questions regarding this part here? Yes, maybe, yes. Why it's log 10? Because actually when we deal with logarithm, this logarithm, it has different bases. Do you remember when I told you, for example, just a minute ago, I have a class of 16. I want to divide it into 2 parts, for example. Okay, when I divide this 16 into 2 parts, we call it log of base 2. Okay, and we write it something like this, log 0.2, for example, it means log of base 2. But he said, I don't want to divide this into 2 parts. I want to divide it into 3 parts. If you divide the initial one into 3 parts, then you're not talking about log of base 2, you're talking about log of base 3. If you divide it into 4 parts, then you're talking about log of base. If you divide something into 10 parts, it means of base 10. By default, they divide it into 10 parts, and that's why when I use the calculator and I said log, automatically they said as if I'm writing log of base what? 10. So what does it mean log 10 here? It means, hey, when I give you x, apply a logarithm of base what? Of base 10. So divide x into 10 power 10 until you reach actually the value 1. Okay, clear? Any other questions? Yeah. Can I do what? Yeah, okay. Oh my God. This one, yes? Okay. Yeah, if I ever. No, this one is apply for only the number 2, yes. If applying that to the 2, it's not going to be worth it. We apply only for 1. If they, yeah. No, 2, it means that you're minimizing this and you're getting the same graph, but instead of big scale, it's going to be, okay, apply it into 1. Yeah, somehow normalization of one of these fields. Any other question? Okay, this one is just, I want you to know that one, when you see that you have a numeric which is big and which other one is small, what do? You want to capture whether there is a relationship between them or not. Apply the logarithm transform to the big using this method that I have already given you, and draw the graph, and you will see that these graphs is going to be what is going to be, if there is a relationship, it's going to be much clearer than if you leave it like this. Okay. So when we do a plotting of these graphs, and I have, do you remember when we said that a 0.1, 0.2, 0.3, point x and y, and I have given you for x equal 1, y equal 2, for x equals 0, y equal 1. Do you remember all these things? So if you have a very large number of points to plot, or our numeric variables are discrete values, then it's possible that using a scattered plot straightforwardly will not be informative. I have millions of points, and the millions of points are already, you can see them in front of you, but I can get nothing from them. The visualization will suffer from overplotting because I have 0.1 and 0.2, they are as the same point. So I will have only 1 point, but overplotting. Is this clear what I'm saying? I will have overplotting where the high amount of overlap in points makes it difficult to see the actual relationship between the plotted variables. So how to resolve this? Again, a question in the exam. If I have millions of points, yeah, Khadija, now when I say this, Khadija is going to ask me to repeat this, yes, Suad, again. So I have millions of points, and I'm doing what? I'm using the scatter plot in order to plot them. As you know that these points may be overlapping. So how to resolve this problem? one of these three things. Actually, if we want to use what? A scatter plot. One of these. The first one is sampling. The second one is transparency and or what? Jitter. So what do we mean by this? Sampling, as the name indicates, it means what? Instead of having 1 million, take a sample of this, random sample of these numbers. So instead of making it 1 million, let's make it 1,000. Okay, that's what we call sampling. And actually, it's not that much. We do sampling in other type of data, but not here. Okay, it's not that much recommended. The second thing is transparency. What do you mean by transparency? Transparency in that I have these set of points. So if we have points depending on how many number of points are overlapping. What does this mean? It means that we have a point, we give it a light color. We'll see. Actually, do I have something here? So as you can see, this is what this is a scatter plot for this variable 1 and variable 2. And here, what do we have? We have included this alpha. And do you remember when I told yesterday, actually, I talked about alpha, and we said this is a transparency. So as you can see now, not all these colors, they have the same saturated color, yes? Some of them, they are lighter than others. Why? When you look at this point, it means that I have so many points that collide here. While this point here, I have 1 point or less points. Is this clear? So now you can differentiate between where the data is, like the points are overlapped or the points are not overlapped. And even this is not that much actually informative. So that's why we use something called a jitter. Jitter, it means that we inject some random data to this in the graph. We inject some random data to the graph. It means that this point here, what do you think? We have 1 point or many points? Many. So what they do, they just like, since these points are confounded in each other, they overlapping, they say, you point, you move a little bit like this, and this point move a little bit like this. And this, so we will have like, it's not going to be exactly in its place, it's going to be a little bit. That's what we call what? What we call this, guys, a jitter. Okay, so we have this regular plot and X jitter, Y jitter, and here the alpha, actually this one, as you can see, this is in the PLT, while this one is the seaborn. In the seaborn, it doesn't take alpha as an argument directly like this, and that's why we have to put it in a dictionary, and then the alpha is going to be 1/1/3. It means that transparency. We know what does it mean alpha, yes? Do you know what does it mean alpha? Transparency. What does it mean transparency? Sometimes in a design or in a video, for example, there is this image and you can see what's behind the image. This is what we call transparency, and we use this a lot in Adobe Premiere, Adobe After Effects, all these things we use it. So we'll have something like this. Sorry? Yeah, here we're moving it a little bit, so it's not about the accuracy. Yeah, but these are just for visualization. When we add these jitter, the actual values are going to stay as they are. Okay, so this point will not move from its place. But just for displaying this, so here, as you can see here, if I leave it like this without the jitter, what's going to happen? All these points are going to be confounded. With this jitter, you know that there is like 1, 2, 3, 4, 5 points are there. Yes, questions, guys. Ask me. Yes, Mohammed. The jitter is, look, this one here, when you look at this one here, at this point here, okay, as you can see from this point, the color is not light, the color is, this means that I have many points, they are overlapping, okay? Many points, they are overlapping. If I have many points, they are overlapping. Can you ask these points, each point of them, that be displayed a little bit so I can see how many points? That's where the jitter is gonna come. And as you can see, what did I say? I say, look, if we have points that are overlapping, these 2 points are overlapping, randomly move one to the x-axis 0.2 and the y to 0.2. So what does this mean? This point and this point confounded. Okay, now when I use this jitter, what's going to happen? One of them is going to move like this, the other one is going to move like this. So when you look at them from your perspective, how many hands are you saying? Let's say 1. When I move this or this like this, you can see what? That's exactly what's happening here. Look what happened. Before, I had only 1 point here. Even though the color is like a dark color, but I can see only 1. How many points behind this? How many points are overlapped here? You can use this jitter in order to. Okay. So even though the count is not going to be that much. Yeah.
We have to wait.
We can just let's go one by one. We can exactly count the number of these. We can. Heat map. Heat what map? So for now, what we have seen for now, anyone can summarize what we have seen for now? So a scattered plot, and this scatter plot is gonna do what? 2 variables, numeric variables, x and y, and we're gonna plot these points. When we have a lot of points, what do? One of 3 solutions. What are these 3 solutions till now? Sampling. It means that instead of taking all the points, let's take a random sample of them. The second one is transparency. It means using alpha. So if I have a lot of points, they are overlapping, and the points that are not overlapping, I change the color depending whether I have a lot or not. And what is the third thing? The jitter. And we said that we inject some randomness to go to the x-axis or y-axis. Is this clear? Okay, now we go to another type of visualization, which is called heat mapping. And heat mapping is a simple idea. So I will have it's an alternative to a scatter plot. It's an alternative to scatter plot. The values of 2 numeric variables to be plotted are placed on a plot axis, similar to histogram. The plotting area is divided into grid. You know something? Let me show you something here. Yeah, here. Let me show us. Look at this part here. So this one, what we had before, if you remember. Okay, this is variable 1 and this is variable 2, and these are the points. Do you remember the one that you asked me about? And this is the heat map here. Okay. Look at this one here. This one, by the way, these 2 are the same, but now I'm using colors. When you see this one here is the color bar that is gonna give you an indication whether I have a lot of overlapping points or I don't have. Okay, so let's look at this grid here. Grid 4, 6. Can you see 4, 6? I'm gonna put here, let's say, yes, let me. So 4, 6, which is, this is a 4, and this is a 6. So in this here, what do you think? I have a lot of points collide or I don't have? So look at here, as you can see, this is a scale. The darker here, it means that I don't have that much. When I go to a lighter, it means that I have a lot of collide. Is this clear? So when you look at this now directly, look at these colors, it means that I don't have that much overlapping or points. Okay, this means that do I have points here a lot? What about here? No, what about here? What about here? Yes, what do we call this? Heat map, that's it. So I can look at, that's why it's called heat map. If you go and you do some radiology or these things, okay, brain, for example, activities, and these, they put these props on your brain, and they can see if you, for example, you're trying to remember things, where is the part of the brain that is activated? Okay, you're sleeping and you're having dreams, bad dreams. There is another part of your brain is that activating, and they can see this because they have this heat map in front of them. Okay, that's actually why you can go to the hospital if you don't have anything. No, right? Except, for example, Rad is sleeping now. Which part of the brain, I'm not kidding, which part of the brain is working and which part is not working? While you're dreaming, there is a part. And this part here is when you want to know the part that you're gonna lie, when you lie or you say the truth, this is the part that is, this is what we call nasiya, nasiyatun kazibatun khatiya. That's why it says nasiya, because this is a part that actually is responsible for saying the truth or lying. So if you go and put and you're lying, they can detect from this one here, Muhammad. Okay. So this is what we call what? A heat map. Questions? So how do we draw this heat map? Let me go back now and show you. So now we understand a little bit. So I have this one here and this one here. So instead of having these here, I will have what? Color. This color is going to depend whether I have a lot of points that collide or no, I have like no points. As you can see here, do I have any points? That's why it's what? Dark. And I need to like know the bin here. So what does it mean, the bin? So is this curve here, I want to have this rectangle, I want to have a width and a length. We'll see how to do it. But this is the whole idea. Where is it? I guess back. So similar to histogram, the plotting area is divided into grid. The number of points in each grid rectangle is added up. I have more points, it's going to be lighter. What if I have more points to be darker? We reverse it. So there is a way to reverse it. Instead of having it lighter, we can have it what? Darker. So there is a way. Since there won't be a room for bar heights, count are indicated instead by a grid cell color, heat maps for. So when do we use it? Quantitative variable versus what? A variable. Good for discrete variable for also. Good alternative to transparency for a plot of data. So these are important things. So I can use heat map for quantitative versus quantitative, discrete variable versus discrete variable. Okay, how to use it? This is how to use it. I'm gonna show you quickly. Sorry. Yeah, this subplot because I want to show you both in the same graph. I want to show you both in the same graph. And as you can see, this is the subplot 1, 2, 1, and this 1, 2, 2. Okay, so this is 1, 2, 1 and 1, 2, 2, and I want to show you both of them. So let's look at this one here. So scattered plot of discrete data, the thing that we have seen before. If you remember the jitter, X jitter, Y jitter, don't include any fitting line, and the alpha is 1.3. And the second one is what is the heat map, and that's how we write it. PLT dot, but instead of hist what? 2D, because it's similar to histogram. If you remember it, it's one bin, these bins in front of each other. Now I have this 2D. And what do I do with the data as it is? And what do I have here? The X and the Y. And what do I have here? A list of variables. And this is, do you remember when we said the minimum, comma, maximum plus 1, comma 1? Do you remember this? Yesterday. We said how we determine the number of bins. By the way, there is another way to determine the number of bins. I can give it to you. You know something? Let me give it to you. So there is another way to. I will give you this. What is this? I was solving the assignment. It seems. No, this is something else. The assignment. Okay. No, I don't expect you to do anything. It's up to you. Okay, guys. So how to determine the number of bins? I want you to pay attention to this one. I have written this method for you that is gonna give you, I'm gonna give it to you, so don't worry. You don't have to take pictures. What does it mean, Andy? Okay. So look, what do I have here? NumPy dot percentile, if you remember, and I want the third one and the first one. So I want the 75 and so directly, if you give me a column in a data frame, I'm gonna get what? I'm gonna get the Q3 and the Q1 of that column. So this is the first step. The second step is that I'm gonna get the IQR. The third step is that I'm gonna get the width of each bin, and the width of each bin, this is formula. This is one of the best formulas till now in statistics that has been used in order to find the number of bins. And it says as follows: the width of the bin, the width of the bin is equal to 2 times IQR, and we know how to find the IQR, times the length of the data frame that we have, the length of the column that we have, power what? Minus 1 over 3. And this is going to give me the width of each bin. Sorry? So this means that H is equal to 2 times IQR multiplied by N power minus 1 over 3. What is N? Is the number of rows that I have. Clear? So this one here, length of DF, it means how many rows do I have? Multiplied by, not multiplied, it's power. Because I have how many stars? 2 stars. So star, it means power. Power what? Minus 1 over 3. This is the formula. So this one is the formula that's given. This is to find what? The width. What is the number of bins? It's the maximum minus divided by the width. Okay? This is the best way to find what? The number of bins. Till now. We're talking about each column. So when as you can see, when I asked to find for me the number of bins for the column humidity, now is going to give me this. The column count now is going to give me this. Sorry? Because if you leave it, this one here is going to give you 36.8. Okay, what do you want? You want actually to be the maximum, not the minimum. So you don't want 36.8. This is not number of bins, it should be an integer, and that's why actually I incremented by 1. Yeah. 3.234. Okay, that's why I put C. Okay, guys, so one of the things that you can use is this one here in order to find the number of bins. Yes. Yeah, you can do this. You can do this. It's up to you. Okay. So you can see this one here. So we have arranged the number of bins for X and the number of bins for Y for this question. And then all what we need to do, how to draw a heat map, guys. What do we use? PLT dot. The same histogram that we use, but now what do we add? 2D, and that's actually the variables. Clear? Heat map can also be used as a to-do versions of bar chart, plotting on combination, two categorical. You're gonna see something like this. Do you remember when I told you that we can reverse the heat map? Do you remember this? So look at this one here. What did I do here? I said, draw for me a heat map. Okay, pay attention a little bit. Draw for me a heat map. This is the data that I want to use. This is actually the x-axis, and this is what? The y-axis. Clear till now? And this is the bins, the same thing that we have done. And I said now, the heat map, I want it to be, we have a lot of colors here that I want it to be vivids underscore reverse. What do I want it to be? Vivids underscore what? R is reverse. When I say reverse, as you can see now, the lighter color is going to give you what? The lighter color is going to give you a high number of points or a low number of points. Look at this one. What do you think? This one is low, and the darker color is going to give you high number. Let's look at this one here again. Look at this one here. I think I have one here. No, let's look at this one here. What do you think? What do I have here at 9? The lighter color or the darker color? What do I have at 9? Look at and here 0, the darker. Clear? Let's look at this one here. What do you think? What happened here when I said vivids underscore R? What's happened? The reverse. Which one? Yeah, this. Yeah, there is a color code. Okay, and you don't need to remember this. Okay, but underscore R, what does this mean? It means that reverse. Now look what's this one here. Cmin equals 0.5. What does this mean, Cmin equals 0.5? It means I want to color for me anything that is greater than 0.5. It means that at least I should have how many points? 1 point. If I have 0 point, do I want it to be colored? And that's actually is here. The Cmin parameter specifies the minimum value in a cell before it can be what it can be plotted. And by adding Cmin equals 0.5 parameter, this means that the cell will only get colored if it contains at least how many points? At least 1 point. Clear? What does this mean? Below is gonna be 1. Okay? So as you can see, these points here, it's not going to be colored because it contains what? 0 points. Okay? Clear? Okay, good. So now, some additional variation. We said that if we have a lot of data, you might want to add a notation to the cell. And this is going to answer your question. In the plot indicating the count of the points in each cell. Okay, indicating what? And what does it mean? Remember when we said that darker light, for example, in this one, darker light, it means we have more points in this grid in this cell. Okay, how many points do we have? We can use this. It's not a big deal to you. I will not ask you to do this, but I want you to show you the result of this one. So what does this mean here? How many points are in this grid? 8. And what does it mean? I have 9 points here. So as you can see, between 4 and 6 here. In this grid here, in this area here, I have how many points common? 9 points. How many points are overlapping, for example? How many? 9. Is this clear, guys? You see what does this mean? So I can give each count, and as you can see here, the 0 is not going to be counted. Okay, so we can have something like this, and you will be able to deduct very easily that between 8 and 0, we have only 1 point. So in the code, this part here is what we have done. This part here is for annotation. Okay, they move through the x-axis, the y-axis, as they do some counting. And here, what this part is, actually, this is the same. Okay, pay attention a little bit. Let me explain this. This is actually the same, but here it depends on the color of the number that we want to use. If the number, if this grid here is dark, they want to put the number in white. If this one here is light, they want to put the number in black. That's all. Okay, so they're gonna put the number, as you can see. They are saying that if C greater than or equal 7, put it in white, because the cell is gonna be dark. If it's greater than or equal 0, it means that it's less than 7, it means, but greater than 0, put it in black. That's actually why I have some numbers here, as you can see, in black, while here I have numbers in white. That's what this is. Okay, clear, guys? We're gonna go now to volume plots. So there are a few ways of plotting a relationship between one quantitative and one qualitative. One of them is what? Violin plot. Is one of the lower level of abstraction. For each level of a categorical variable, a distribution of values on a numeric variable is plotted. The distribution is plotted as a kernel density estimate, something like smooth histogram. We'll see what does this in a minute. Don't worry. So these are called what? Seaborn volume plot function. And as you can see, I have SNS.volume plot. I have what here? The data. What do I have? The x-axis is going to be categorical. What is the x-axis? And what is the y-axis? Numeric. As you can see here, what do I have? I have alpha, beta, gamma, and delta. Let's say I have 2-cylinder, 4-cylinder, 6-cylinder, and 8-cylinder. And what do I have here? Maybe it's the consumption of fuel. Maybe, let's say, these alpha, beta, gamma, delta, maybe these are the name of basketball teams. And here we have the scores. Okay, here we have the scores. Let's say the scores. And if we talk about the scores, if you look at this one here, for example, what you're going to say, most of the scores, let's say instead of 10, we have, for example, instead of 0, let me write something. Let's say instead of 0, I have 30. What do I have? 30. And this one, let's say, instead of this, let's say I have 70. So 70, and this one is, let's say, 92, and this one 104. Something like this. Okay? So in average, for example, for this basketball game team, which is alpha, what do you think? Most of the data are where? So you look, let's say we said this is 70, and let's say this is 50, for example, something like this. So most of the data are here, for example. While this one also, most of the data are here. This one, most of the data are here. This one, most of the data are here. But what about this one here? I have a lot of outlier data. Can you see it? Some of the games are above 104. They score above 104. Some of the data are below, for example, 30. Here, most of the data is around 70. Okay, guys? That's what we call. So it's the same thing that we have seen before. What does it mean, the same thing that we have seen before? It means that we have these dot points here, these dot points here, these dot points here, and these dot points here, for example. Okay, this is for alpha, this is for gamma, this is the score. So instead of having these points, we're going to draw something like this. That's what we call violin. Okay, and I can, as you can see, there is something inside this violin. We're going to talk about it and how to get rid of it or actually include it. And what does this mean? But it's the same thing as points, but now I'm having this violin. And each of these is going to have a meaning. We're going to see what this means. So how to draw it? All what you need to do is to put the data. The X is going to be what? Categorical. And the Y, numeric. And we can actually inverse this. We will see how to do this. But this is an important thing. When you have a categorical data with a numeric. And this is important. And these are actually some few of the plots that you can use. You can see that the numeric data takes a different shape in each categorical. As you can see, these are the numerical data at stake. This is a miniature box. This one here is the plot box that we have seen, if you remember. Plot box, what does it mean, plot box? The medium in the middle, and then we have the Q1, the Q3, and we have the minimum and the maximum, and anything outside what? Q1 minus 1.5 multiplied by IQR, or Q3 plus, these are called what? Outliers. So as you can see here, what do I have? It draws this for me, and the color is this one here, and the inner, can you see here? You see this here? Do we have anything here? No, this one, the inner, get rid of it. And what is the inner? You will see in a minute what is the inner. So the inner is the plot box. This is the inner. You see this one here? These are what? The inners. What do I have here? What is this one here? This is the medium. Okay, what is the medium here? The white button. What is this here? Q3. What is this here? So when you look at this one here, you would be able to tell me that this what is what? The medium. This one is Q1. What about this one and this one? These are the edges of the outliers. Anything outside is going to be what? Outliers. These are the edges for the outliers. Anything outside is going to be outlier. What do you think? Do I have outlier here? What do you think, guys? Can you see these points here? They are outside what? This edge. What does this mean outside this edge? These are outliers. So just by drawing this, I would be able directly to tell whether there is outliers or not. I don't have to do all these calculations. Is this clear? So how to draw this one here? We use something called box plot. And a box plot is another way of showing a relationship between a numeric variable and a, compared to the volume plot, that lands more on summarizing on the data, primarily just reporting a set of descriptive statistics for numeric values on each categorical level. A plot box can be created using a seaborn, and this is actually the seaborn here that we're going to use. So this one here, as you can see, SNS dot what? Plot box. What do I have? The data. This is the categorical variable, and this is a numerical variable, and use this one here. And by doing this, I'm drawing this one here. And when you look at it, you can tell me directly that I have outliers in which one of these categorical variables. Which one of these it has a gamma. Clear? Is this clear, guys? From the top and the bottom of the box, these are the whiskers indicate the range of the first. This is actually what I have told you. So these are the range. This one is what? This one is what? The Q3, yes. This one is maximum. This one is minimum, yes. Yeah, it's going to show you the outlier, yeah. It's going to show you the outlier, yeah. A maximum range is a set of the whisker lengths. By default, it's going to be 1.5 times IQR. For the gamma level, there are points below the lower whisker that indicate individual outlier points, and that's why actually we have them. Okay, guys. So as you can see, just a single line of code, and I would be able to detect directly whether there is an outlier in one of them. Okay, but as you can see here, this one here, what do we have here? We have two categorical data with a numeric data. Do you remember when I told you that we can draw them in the horizontal and on the vertical? All what we need to do is, so as you can see, x equal, the numerical now, while before, as you can see, x equal, okay? So, and we'll have something like this. Questions? Sorry? This one here? If you remember when we have this set of colors and so we have chosen the first one. By setting the inner equal quartile, do you remember when we said the inner equal 3 lines will be plotted within each violin area? And what are these 3 lines? What do you think is going to be? Okay, the middle and the what? Q3, and all what you need to say is this one here, inner equals what? Quartile, and you would be able to see these quartiles. A lot of things. Cluster bar chart. What time is it now? 6:20. I promise you, within 20 minutes maximum, we'll be all leaving. So don't worry. Hopefully, what is the slide number here? I don't know. By all means. Cluster bar charts to duplicate the relationship between two. That's why, guys, again and again, you need to know when to use these things. You need to know what is the type of the column, the data that you're dealing with. We can extend the univariant bar chart seen in the previous lesson into a clustered bar chart, like a standard bar chart. We still want to duplicate the count of data points in each group. So let me show you what do you mean. Look at this one here. Okay, we have experiment A, experiment B, and we have what? The control experiment. So this is category variable 1, and this is what? The count. The count of what? Low, medium, and high. So we have category 1 and category what? 2. And inside category 1, we have the control. For each control, I have low, medium, and high. So look at this one here. How to draw these? So the control, the experiment 1 and the experiment B, how to draw these? All what you need to do is something called count plot. And what do we have? The X is, and the hue, this one is for the count. And what do I have now? If I look at this one here, can anyone tell me what you can conclude from these? All 3 of them somehow are close to each other, except this one, it has what? This one and this one, they have high count than this one here, which is what? Again, I'm gonna repeat this. As you can see, all of them, they have somehow similar when it comes to the low. As you can see, the low is somehow similar. The high is what? This one it has what? A higher high than control and experiment B. Okay. What about the medium? The medium is, the high is the same one. Okay, that's how. So the first categorical variable is indicated by the broad x-axis, control experiment A and experiment B. Within each group, this is important, there are 3 bars are plotted, 1 for each level of the second categorical variable, which is low, medium, and high. Color differentiates each level and is documented with the legend. And this is the legend here that we have. The plot tells us that the 3 categories are fairly balanced in frequencies across the categorical variable 2 appears. So as you can see, experiment A group appears to have slightly lower counts of the median points, the orange central compared to the 2 others. Sometimes we can play with the legend. As you can see, this legend here, I didn't like it. So we can put it somewhere else. And that's actually how to do this. Okay, now the legend is here and you can check. Alternative approach, we're almost done, I promise you. So again, if you remember, we said the heat map, we can use it also for two categorical variables. Okay, that's what to say. One alternative way of duplicating the relationship of two categorical variables is also use the heat map. The heat map that we have seen before, now we can use it also. Heat map were introduced in this using 2D version. The seaborne function heat map is at home, which is a type of map implementation. Instead of providing the original data frame, we need to summarize the counts into matrix that will be then plotted. It's not going to be easy, but I will do my best to. Yeah.
To draw the but to make it more clear, we use the heat map.
No, it's not to make it more clear. It depends. Maybe I have a few data and the scattered is actually better. Yeah. Yes.
But then we're using the heat map.
Yes, we can do this, but we cannot do it directly. We need to do to change. As you can see, instead of providing original data frame, we need to do some summarizing of the counts before we apply this. And how we do this, I'm going to show you. By the way, guys, maybe we go here, for example, and let me write something like this for you. This is actually is going to be, because you asked me this question. Let's say Python heat map correlation. So one of these heat maps, you can see these are all heat maps. You can, the same thing that we have done, but you can use the correlation. Let me show you, it's here somewhere. So as you can see, this is the seaborne, and this is the data frame, correlation data frame. And as you can see, what do I have here? So find for me the heat map. And what do I need? Dot what? Dot correlation. And this is actually the correlation between these numbers. But I can do, I don't know why they don't have, yeah, I can show you the correlation now just in front of you. Overall quality with the sale price. What is the correlation? 0.8. Where is the correlation is going to be 1? It means that perfect correlation. Can you see this one? Look, overall quality with, or quality, this is a complete correlation. What do you think? Look, let's say garage area with what is going to be perfect correlation? Remember, these here are the same as these here. So garage area with, can you see it? So this here is going to be what? Where do we have, for example, a negative correlation? Something increase, the other one decrease. Where do you think? Can you see them? Wherever I have negative, it means that something increase, the other one decrease. Let's look at, for example, this one here. What does this mean here? The overall quality with the external quality, they are what? Inversely proportional. Okay, let's look at this one here. Year recommended with what? With, let's say, kitchen quality. These are inversely proportional. Clear, guys? So we can do this using what? As you can see, we have a heat map, and here they have done some annotation, but with this one here is enough to draw the correlation and find the correlation. And directly you would be able to say, oh, look, there is a huge correlation between this one and this one. Directly you can say. Okay, guys, so you can draw this and use the seaborne to draw the correlation. You asked me about the, you know what does mean correlation? The R, the one that you are. This is Pearson correlation. This is what the R. So if I ask you, is there a correlation between year remodeled and the HS whatever 3 car and you look at the number here, and you see that the year is 0.3, it's close to 0, it means that weak correlation. Is this clear? That's what we call Pearson correlation, R. Okay, guys? Questions? So instead of providing the original data frame, we need to summarize. Actually, we're not going to use this, but I'm going to explain it to you. And this is the last thing today, I guess, unless there is something that I have. So we have two categorical variables. We cannot put them in a heat map. So what we're going to do, we're going to group them and then get the size of these categorical variables. Get what? The size. The second thing is I'm going to do something called reset index. And then after I do a reset index, I'm going to do something like pivot. And what does this mean? Look, what does this mean? So I want the first part, this part here, although I'm telling you, this is not just, I want to show you this, but it's not like you don't need to do this. The heat map is going to take what? Is going to take an array, a NumPy array that contains value. It will not take these categorical variables. So I need to summarize the data in a NumPy array and then send it to the heat map. So all these steps, all what I'm doing is I'm summarizing the data. Okay, that's what I'm doing. Look at the first one here. What I have done, I said that, look, group for me the two categorical variables that I want to draw. And give me the size of this and put it here. After that, I want to do something called reset index. And this is actually another function that is going to take the name of the count that I have in order to do something. It's creating an array of these values here, of the count that I have here. The last step is to do something called pivot. It means that convert the row into column. And here, the index is going to be this is actually the row, and this is the column. The category variable 2 is going to be the row, and this one is going to be the column, and the values is going to be the count that I have. I will show you an example. I guess I have an example for you. Yeah, that's yeah. Then we're going to take the values and then we're going to stick it here. The heat map tells the same story as the cluster bar. The similar colors across the rows suggest that the category 1 group sizes are similar in size and distribution and blah, blah, blah. So usually we'll not use this, but it's there. These are 3 steps we need to do them before we apply the heat map into 2 categories. And usually we don't do this. This is what an experiment. A has slightly fewer counts the medium. Again, they have done this. It's the same thing here. Alternative approach. Here the annotation equal true in order to find what? Annotation is equal true in order to find in each cell what is the number. And this FMT means that the annotation will be all formatted as integers. Usually it's a string. It's here. I think it's covered here with this one. Let's go back here. Again, I'm moving fast on this because it's not that much important. So as you can see, usually by default, it's what? It's a string. But if you want to put it as integer, what do you put? FMT formatted as D for integer. If you leave it without thing, it's going to be so if you want to format it as a float, you put 0.05. Okay. So if you have any cell with no counts in order to account for NAN. So I guess that's it for today. Do I have anything else? Oh my God, I still have. And this is important. I'm really sorry, guys. And this is important. Okay, line plot. No, let me go through this one here. Yeah, I guess I can see all of you actually are sleeping, except Khadija. So a line plot is fairly common, a plot type that is used to plot the trend of one numeric variable against the values of the second variable. So let me Y lines instead of bars to emphasize relative change, emphasize the trends across X values. So this one here, let me show you. Oh my God, what is this? I'm gonna use, look what I'm gonna use this part here to show you what do I mean. So let's say I have a data something like this. I have a data like this, okay? This is a bar chart like this. So I want the trend line. I want you to pay attention a little bit, guys. I want a trend line. What do I do? Remember, this is a bar chart. It means that in this bin, these are the values, yes? In this bin, these are the values, yes? Let's say this is 6, this is 10, this is blah, blah, blah. So what do? I take the mean of this one here. So 1 point. For the whole bin now, I take this one, which is, let's say, and what do I do now? The next step is, for the whole bin, I take only, and for this one, I take 1. And this for this, all these I take 1, and this one I take 1. And now the trend is going to be something like this. Connect the points together. That's what we call what? This line here is the trend line that I have told you about. This one. What we call it? Line plot. If there are multiple observations in the X bin and the Y value, what do? We summary, like we take the mean or the median. The plotted points are connected with a line that emphasizes the sequential or connected nature of X value. The same thing that I have done. Is this clear? So why do we need these lines instead of bars? Emphasize relative change. Whenever we have relative change, we use this. Emphasize trends across X values. And how we do this? We do it actually with something called error bar. What do we call this? Error bar. And this error bar actually is going to take the data, is going to take the X, and is going to take the Y. And when we do this, as you can see here, what do I have? I have a disaster. I have what? It's not supposed to be like this. So we need to fix it. We need to do what? To fix it. And how to fix it? Yeah, this line is going to do something. And how to fix it? What happened? That's how to fix it. What do we do? Let me show you what do we do. So now is, do you remember the number of bins? The same thing that we have done. And this actually the centers of each bin. I'm going to take the centers of each bin and compute statistics in each bin. And that's how we compute statistics. We have this cut function. Anyone remember? Have I told you about this cut function? Never, yes? Okay, have I told you about mean? I guess yes. And the standard error, mean. I haven't told you about standard error, mean. Mean, no? Okay. Oh, not done. Not done. I can see actually all of you.